So today last time we talked about parametric amplifier, okay, and then today it's very natural we put that amplifier, okay, in between a pair of mirror, okay, cavity. It's a terrible drawing, but. And from previously, we know that if you put a amplifier into a cavity, you can make a laser. Okay, so this is a similar case. We want to make a laser is also called oscillator. Okay, so we want to make an oscillator from this structure, and then the input this time is a pump. It's typically like an optical pump. It's no longer electrical pump. It's omega 3. Right. And then if your input is on resonance with the frequency of your cavity, okay, laser cavity, then your light will build up inside. Your light can build up inside. It's just as simple as a Faber Pro cavity. And then this will trigger omega 1 and omega 2. Right, as we said before, this process is from one photon from omega 3 to a photon in omega 1 and the other photon in omega 2. And because it's a mirror, right? So all these photons will be reflected back. And this omega 1 and omega 2 will act like, will trigger other photons also emitted from omega 3 to omega 1 and 2. And then this process continues, and then a field can be built up. And for any laser system, you can imagine that there's a threshold condition, right? So the threshold condition is similar as if you generate one photon at omega 1, okay, does it trigger another photon, or does it decay to 0 photon? Right? Do you have enough gain? In other words, do you have enough gain to let this photon trigger another photon before it decay? Right? Otherwise, you would just have, on average, you just have one photon inside your resonator. And it's, yes?
So when you say it triggers the down conversion further, what is exactly happening there? Like what is the physical process? Like
you mean the frequency?
Two photons get reflected from the second mirror.
Yeah. So it's from last time. I think we write this down. Z. Let's say E1. This one is proportional to E3 times E2. Right. So if you have a photon, a real photon there, the E2 is larger.
Okay.
Right. So you have more photon and you have more gain. Typically, that's what you get. I know we're thinking it's always there's some vacuum fluctuation there, right? Yeah. For vacuum fluctuation, just give you the first photon, okay, and then you need it for the second one, the third one, and then this one can grow, and your gain become very large. Okay.
Yeah, like equation-wise, it makes sense, but like, what sort of process is it? Like stimulation?
Yes, it's more like stimulated emission. Yes, instead of spontaneous. It's the same as a regular laser, right? When you're below threshold, then your gain material will have some spontaneous emission that gives you the initial photon.
Yes.
Okay. But then when you're above threshold, then you're stimulated emission.
Okay.
Yeah. So this is the same thing here.
Okay.
Yeah, so it's a very nice question. So if you're staying in a spontaneous emission regime, on average you just get some noise. Okay, get some noise or very few photon. If you're above the threshold, if this photon is able to increase, well, because of whenever you have one photon in omega 1, you also have a photon in omega 2. If this is able to increase the photon generation rate of omega 1 and then generate the second one before the first one escape the cavity, then this process can build up, right? One photon leads to 2, 2 leads to 4, and 4 leads to 8, and then they start to oscillate. Okay? So you can imagine when we do this calculation later, there will be a term showing up as something has to be larger than your loss. And this would be your threshold condition. You can almost guarantee to have something like this. Okay, and there's actually many ways to calculate the threshold. Okay, maybe let's first do a picture here. So what do we mean by threshold? Okay. Usually in laser, the threshold is the current you put into your laser, right? The more current you put, the more population inversion you have. Okay. For optical pump, the threshold is usually on your pump, on your input. Okay. So it's very clear here. The emission rate are mostly relevant to your input. Right. Last time we also solved the parametric amplifier, and then I think we arrive at the equation like this. Okay, your E1Z, right, have exponential increase. That's your gain, and then I believe this gain is proportional to E3. Right. So E3 controls the gain of your system. Right. If E3 is higher, you have more amplification. You have more photon. Okay. And so what will happen if you're E1? You can expect. Typically, you will first have. Well, you can have below 0. So okay. Okay. So we just have some noise below threshold. And then there will be a critical point where this gain in your amplifier is very large that it can overcome the loss in your cavity. Right, the loss could be this mirror is not perfect. A portion of the fiber will emit. Also, these two might not be perfectly aligned. So when the photon get back and go into the crystal, it can scatter outside. Okay, so there are all kinds of loss here. If your E3, the pump, is large enough, then you can create a huge gain to overcome this loss. Actually, we can make a prediction here. I would guess this is larger than alpha. That's a threshold condition, right? This is a gain, and then you have a loss, gain larger than loss. You get lasing. Okay. And I believe this one. Not sure if it's linear, but probably. Okay. So it would just act like a laser. But the equation here is a little bit complicated than the laser. Before we proceed, any questions about this picture? It's very clear, right? We're making a laser here. Okay. So I want to remind every one of you how we convert an amplifier to a laser. in the previous equations, right? In I think in this is what we have in amplifier, fiber amplifier. Okay, you have Z, and then we say in an oscillator, in a fiber cavity, you're not watching the position, right? You're watching the output of the mirror. So instead of seeing a laser, instead of seeing your light propagating along the waveguide and then gaining its power, you're watching the time dependent of the power coming out of this mirror, right? That's the thing you measure. Okay. So there's a change you need to make is to convert from position dependent to time dependent, right? Because the thing you measure change. And also because the dynamic inside change. Okay? In waveguide or in fiber, it's one dimension. You propagate there, and then it's there. You never come back. Here, you propagate, you come back, you propagate, you come back. So time is the natural coordinate here. And to do that, we say there's an easy way. It's because the position, if you patch them, okay, you just consider what's the distance you travel instead of the absolute position, the distance you travel. Okay? From here to here is L. When you travel back, the distance you cover is 2L. Right? And then again, 3L, 4L. Okay? So take this as like a waveguide as a distance you travel, then naturally you will have C times T. Right? Maybe you can add a refraction index here, but for simplicity, we just set it as 1. Okay. So C times T. Okay, and then you simply put it back. All right, this is how we do it in the fiber amplifier and then the laser. Okay, you make this distance to time conversion, and this is actually critical when you I think there's a trend before. Previously, I think in history, usually what happened is you build amplifier, you build something in waveguide first, and then you add a mirror. And then this is, very, very useful. Okay, you can do this a lot of times. Like if you see someone have a very nice paper on waveguide or in fiber, and then you wonder what you can do if you bend that fiber or waveguide into a ring resonator, or you add a pair of mirror to that waveguide, make it into a resonator, then you can do this conversion. Right? Take their phenomenon from waveguide to what you have in an oscillator. Okay? And we're kind of doing the same stuff for in our own research group. 40 years ago, people do optical solitons in optical fiber. I don't know if you guys heard of it, but it's a special effect that when you have a pulse that has a certain profile, a certain power, it can transfer, it can propagate along the fiber like for many, many kilometers without changing its profile. Okay, it will keep its shape. And that normally doesn't happen if you watch the wave, right, the water wave. When you approach the shore, it breaks. And so having a soliton able to propagate along long distance, that used to be very useful for telecommunication. And then Japan actually investigated heavily onto that. And I think US take a different route. US, I think at that time it was, at that time US chose WDM, wavelength multiplexing. And then WDM proved to be the technology, not because it's better, it's because it's simpler. Okay, and at the time there's actually some story, I believe it's ATT, the leading. At that time, ATT right now seems like just like a cell phone provider, but at that time it's really a different beast. Okay, I think the entire market was given to ATT because of a legislation bill. And then so when you do that, ATT has to promise to give something back, right, to the people of the United States. So what they did is that I think in the bill is that they promised to give like 1% or how many of their profit into a research division, that's the Bell Lab at the time. And then so the Bell Lab was actually the paradise for scientists, because you get this funding coming in every year, and then you don't even have to file a proposal for them. Okay, they just come in, you use it. So ATT, people in ATT actually won several Nobel Prize, and then they have wonderful research environment. But I think at that time they kind of I'm not sure if this one, but they kind of make a strategic mistake about whether going into WDM. And then a professor in Caltech who was the advisor of my advisor, he used to work in ATT. They go into a very public, heated debate of which one is the future, and they prove ATT was wrong. And then they lost billions of dollars because of this strategic mistake. Okay, but ironically, right now we're able to do optical solitons in our chip-based resonators. And then people start to think, well, maybe we can use that soliton combined with WDM, both soliton and WDM, to do telecommunication at about 100 terabit per second rate. Okay, that's just imagine how crazy that is, right? Usually your computer is 5 gigahertz clock rate, and then so the application for this is usually a supercomputer. And then, but it takes like 40 years for the soliton to come back into the area. Okay, and then the reason it come back is because we're able to generate soliton from not a propagation fiber, but inside a cavity, a laser cavity. Okay, so here, let's do the same thing here. I think we have in my note, there might be a mistake on the equation. I think I put the speed of light at the wrong place. Let's just work on it. Okay, this one, I only got 1 squared chi 2. Oh yeah, it's actually right. It's not the I think it's this, and then E2. Okay, and then the first thing we do is we give you a loss to this system, right? So when the light travels from here to here, you probably have material absorption inside the crystal. You have some scattering when you come from free space to your crystal, okay? And you also have some loss when the light hits the mirror, because it's not 100% reflection, right? So there's some loss in the system. And let's say there is an average. Okay, the average loss is, just give you a factor there. And now you apply z equals c times t. Right? We apply this. And you have a c multiplied to this side. And we also know this one. Okay. We know this coefficient is 1 over c squared. So you have I omega 1 squared c k1 okay, chi2 E3 E2 So tau, what's the dimension of tau? We didn't even assign a dimension for alpha, so what's the dimension of tau? Can you make a quick prediction by looking at this equation? Time. Yep, correct, right? So because you have derivative of time here, right? So this must be time. So what this means is, if you think about it, this is actually the photon lifetime. Okay, how long the photon? If you don't have this, you just solve this, you will get something like E1 t proportional to E minus tau. Right? It's the average photon lifetime. Okay. It's similar to if you write down something like this. This is something similar as the what we call average propagation distance. It's roughly when you hit 3 dB loss. That's about the distance you go. Okay. So this one, and then well, we probably can simplify this because we know K1 is a function of omega 1 and c. But let's move on to the second equation. Right? We know we have the similar equation for E2. So I'm not going to repeat this calculation. I'll just write down the result. I omega 2 chi 2 c k 2. Okay. So this is, when you look at it, you might feel, wow, this is very familiar, right? We've been solving this equation probably 10 times in this class. But in reality, this is a different type of equation, okay? Why I say that? So first of all, this equation has, in theory, if we're in classical regime, this equation has a trivial solution. It's 0, right? You see here, E1, E2, okay? There's a trivial solution here, 0, okay?
In the first equation, it should be t, right?
Sorry?
You have z's. I think you should have the
Oh,
should be of t.
oh yeah, yeah, that's right. Thank you. Okay. And the second one is just think about usually how we solve equations. When we have something like this, we say we take the root of this one, right? Let's just write it down. Let's just write it as a usual way. Let's see how we solve it. Partial square E1 partial t, right? And then here, these are all coefficient. And then you get minus tau 1 partial E1 partial t. Okay, this is this term. It's all look good. And then you have this. And when you do derivative on this, you can take the conjugate of this one and substitute it back in, right? Just as always. But then the problem, well, let's say there's some coefficient here. We don't know what it is. The problem is this one recover from U1 star when you take a conjugate. This one goes to U1. Okay, so that's good. But this term, E2 star, remains here, right? So the sole purpose of taking derivative of this and then substitute this back in this equation is to reduce the number of variables, right? Reduce it from E1, E2 to just E1, and then you can solve the equation. But it doesn't work here, okay? And then in a lot of cases, it doesn't work that way, okay? Especially in microresonators. For example, this is the parametric oscillation in, from difference frequency generation. There's a similar case in four-wave mixing, Kerr effect. You also see similar equations. And then the other interesting thing is, I think here is that not only, well, by doing this, you cannot solve it. Okay, this is one thing. The second thing I think is actually from these two equations, you will not be able to solve what is E1 and what is E2. Okay, analytically. Okay. So this doesn't work. Okay, but fortunately, if we only care about the threshold, there's a few tricks we can do. Okay, and the first trick looks a little bit terrible. It's you might not even believe it works, but it's the simplest one. Okay, the trick is go for steady state. Okay, so what is steady state? Steady state is, assume you have a E3 and you absolutely believe the output E1 and E2 are stable. Okay, stable in time. They don't oscillate in time. Okay, it's easy to convince yourself of that once you work with one of these devices, right? Like a laser, you know the laser power is stable. Okay, and then here, well, not many people have worked with this, but if you take your hand on this, you can see it's also stable. So the steady state, of course, there's some mathematical way we can justify this later, not just by doing experiment. In steady state, we say it's stable, okay? And then you eliminate the worst thing you have, derivative of time, okay? And then this becomes a super easy equation to solve. And so let's write this down. If this is 0, goes to okay, and then, well, this one is easy enough to solve, right? You can take conjugate of this equation. Right, you can take conjugate of this equation, and then you arrive something like this. It's a little bit strange, right? You have E1, a coefficient of E2 star equals E1, again, the coefficient of E2 star equals E1. So that's exactly why I say you cannot solve E1 and E2 simply using these two equations. But what this equation can solve is solve the E3. That's weird, right? E3 is an input, and now you solve for E3. Okay. So let's just keep working on this. Okay. A simple way to do this, you can just simply multiply these two equations. Okay. This multiply this, and this multiply this. And you have E1, E2 star, E1, E2 star. You cancel them. Okay. So this will give you E3. Okay. It's a little weird. It says that steady state only exists at this input. Okay. Any idea of what's going on here? So guys still remember the laser, the result of laser, right? So when you have output, then your population inversion is actually clamped at a certain level. Right? We call it clamping effect here. So what happened is that, okay, is at first you have E3 at a high level, and you have E1 and E2. We just plot E1, okay, because E2 is just similar. And assume it's above threshold, then what will happen is it grows, right, in time. Okay. Once you generate a lot of photon for E1 and E2, then you lost photon in E3, right? You lost photon here. And what this solution tells us is that, well, there must be an end to this decay, to this loss of photon. So that loss of photon is here. Let's give it a name, threshold. Okay, must decay to this level, and then of course a slow decrease here. This is E1. Okay, it's just like a laser, right? Although you can have very high gain at the beginning, but once the system stabilizes, because your generated photons are using those gains, your population inversion would decrease to a steady level. The same here. No matter where you start, you always come back to here, okay, in a steady state solution. And of course, there's a condition here. The condition is E3 much larger than E1 and E2. Okay, so this one is kind of extravagant. It doesn't decrease that much. Okay? Because once you have E1 and E2 very large, then you need to increase the equation of E3, right? And then you assume steady state, you include that equation, you solve this 3 altogether. Okay. So this is a typical laser behavior. But then how do you know this is threshold? Right, the argument is you can, well, your E3 always decrease once your laser start operating. Right, you're giving your energy to E1 and E2. So to reach this steady state level, you can never start from a lower point, right? If you start E3 from here, it will only decrease. It will not increase to this steady state level. So if there's a laser, if you can have a laser operation, it must start at a position higher than this threshold, higher than this level. Okay, so that's why we call it threshold. And you can already see there's, this argument is not perfect. It's oversimplified a lot of things, but that is actually the correct threshold. Okay, and then if you want to publish paper like using this type of assumption, then the next thing you need to do, well, it's actually hard here, but usually what you need to do next is to assume there's a steady, solve the steady state solution for U1, E2, and E3. In this case, you can't because U1 and E2, you cannot solve it. Okay? And then you give it a little bit perturbation. Okay, you give it a little bit perturbation because it's a steady state, right? You want to show, the idea is that you want to show this is really a steady state. You give it a little bit perturbation, and then you plug it back into this equation, and then you want to show that this perturbation decreases with time. Okay, so it's stable. So that's kind of a standard way when you use this steady state method. Okay. Let's move this equation here. These two. I mean, nowadays, like, people want to make their paper fancy, and they no longer say they use this. Okay, they always put in some linear algebra when they try to solve this type of equation. But in reality, for example, the first squeezing paper using the exact same process, I think it's by Jeff Kimball, right, back in 1987 or somewhere. And I remember in his detail paper, he used this. He simply jumped into, well, here's the equation. What's the threshold? Well, you just assume steady state. Here's the threshold. He doesn't go through those, the crap, we now use nowadays. For example, I'm not sure if I include that in my thesis, but we have similar thing. If you want to solve threshold, then you need to go through like eigenstate and then matrix and then calculate for 2 pages and then get the same result. Okay, and it's not reader friendly, I would say. And we now even have some really crazy method. We call it the Lagrangian perturbation method. I use a lot in my own paper, and that's something similar to this. It's like you probably have a simpler solution, but technically it's not. People can argue you're wrong. So in reality, we always yes. You have a question?
How would you explain the undepleted pump? Like if your E3 field is going down.
Mm-hmm. Oh yeah, because it's just the third equation we didn't include here. Okay, I see. Yeah, because when you calculate threshold, right? at the threshold point, there's actually very few photons there. Does that make sense? At the threshold, below threshold is 0 photon or half a photon or spontaneous photon. At the threshold, it's very, very small number of photons there. So when calculating threshold, you can assume this. You can only use these two equations. That's perfectly fine. Okay. But once you increase the pump, or once you move into a region where your number of photons is increased a lot, then you have to include that third equation. Okay. It's similar to solving a laser, right? Solving a laser threshold, I think we can simply use the field equation inside the laser. But then if you want to solve the entire behavior, then you need to include the equation of the population inversion, right? So there are two equations there. Using the first one, you can solve the threshold. Using the second one, you can solve the entire behavior. Similar here, okay? Okay, so we move this here. Now let's introduce a formal way, okay, to solving this, solving the threshold, okay, and by the way, you guys can see the gain here, right? So right, the lacing condition is this one larger than this, right? But this is loss, right? So if you move all the coefficient to this side, that's your parametric gain, okay? And this is your loss. Okay? So you can get the same thing here, but now let's go into the formal one, okay? So first, we take conjugate of this equation, because in the first equation you have E1, you have E2 conjugate. Second equation you have E2, E1 conjugate. Okay, so it's much simpler if you just take the conjugate, and then you're working with the same variables. Okay.
I think you need to conjugate E3 as well.
Yes, thank you. Okay, and then the next step is a little bit tricky. Okay. So the threshold, what's the threshold? Threshold is above that level, your E1 will grow, right? So you can assume something like this. Okay. It's similar to the equation we have in parametric gain, parametric amplifier. If you grow exponentially, it will look like this. And then this way, so how this will help? Because think about it, this is arbitrary function of E1. It can go crazy, like the wave function can be crazy. This one, we simply we confine ourselves into whether it's growing or decaying. It's similar to the perturbation method. Okay, so if you have the real part larger than 0, okay, then you know it's growing. If it's smaller than 0, it's decaying. So one is above threshold, the other is below threshold. And then, well, you have, again, you might have question like, here we say E1 and E2 are complex number, right? So how would that fit into here? The idea is lambda here is a complex number as well. So your phase change is also included here. Okay. And this only works near the threshold, okay? Because you need it to be at first very small, then it will be exponential growth. And then after it grows a little bit to here, then apparently it's not exponential anymore. Okay. The same apply to, okay. So why the lambda is the same? Because every photon you generated in E1, there's another photon in E2, right? So their growth rate is the same. Okay. Yes.
E2.
Oh, sorry. No, you cannot assume it's 0. Yeah, if it's 0, then everything is 0. Yeah, that's actually the part to prove that there's vacuum fluctuation. Okay, so there's a half a photon there. Okay. I don't know if anyone write a book about what if there's no vacuum fluctuation and what the world would be like. Okay. And then you have, first of all, your iPhone. It doesn't have proximity sensor, okay, because that's vessel laser. Okay. And then, well, of course, we don't have LIGO experiment. We don't know the existence of a gravitational wave. There's no way to prove it. And also, a lot of things really use lasers, and might be an interesting book. And then you can all the way extend to if there's no vacuum fluctuation, maybe there's no dark energy or dark matter. And then the universe would be different. Maybe you can derive a result that because of that, there's no habitable zone in the universe, so there's no us. Okay. And well, that could be an interesting book to some way. Okay. If I ever retire, I can do that. Okay.
So at t equals to 0, you know that E is vacuum fluctuations, right?
Yes, it's yeah. You can actually put in a number here. Yes, yes.
So the very first photon pair is being stimulated by vacuum fluctuations.
Yes, that's right. Correct. Yeah, that's correct. So this is actually a very small number. Yeah. Okay. So now when you see, okay. So now when you put this back in here, okay, it becomes, there's lambda coming out. Okay, we write it in a matrix form. Okay. E1 actually let's do it this way. Okay. Probably the math is actually the same. So I'll keep the t here because it doesn't necessarily need to be E1 0. It could be at a certain time. Okay. Because the vacuum fluctuation itself is fluctuating, so it's not always 0. Okay. So let's keep the t here. The math is the same. Okay. Doesn't matter. This is the derivative of t, right? You get the lambda out in the front. Okay. Then here you have E1, E2. Okay, and you put in this coefficient here, I omega 1 square ck1 chi 2 e3. Oh, no. I omega 2 okay, you get this equation. So you can actually move the left-hand side and right-hand side. You arrive at something like this. Then I omega 1. Missing a minus sign here, yes. Okay, and then okay. So back to the argument here. So this one is 0. Okay, there's two solutions. So first of all, this one, you move it to this side and then combine into the matrix. Okay, linear algebra. So the first solution is very clear. E1 and E2 equals 0. Okay, and that's not going to happen in quantum world. So we know E1, E2 is not 0. Okay, then from let's define this. Okay, there's a matrix. The matrix is this one. Okay, 2 by 2 matrix. For non-trivial solution means non-zero solution of E1 and E2. There's a condition, right? You guys learned from linear algebra that this one goes to 0. Okay. And what is this one? This one is, you multiply this. Minus this 2. This one, I is minus 1. So minus 1, so minus sign. Omega 1 square omega 2. Okay, this is a, yes?
Are the E2 supposed to be conjugated in the lower?
Yes, thank you. So this is a condition for non-zero solution of E1 and E2. Okay. And now you will have a solution of lambda plus minus, right? There are two solutions here. The first one is, well, just all write them down. Chi 2 plus minus C minus tau. Okay, this is a solution for lambda. Apparently, there's a negative solution, right? If you choose a minus sign here. Okay, so that one decay. But there's also a positive solution here, right? Lambda plus is this one. Okay, if this one is larger than 0, you know the solution will grow, right? E1 will grow in amplitude. So you have a laser or oscillator. Okay. And so again, we solve E3, okay? But from this equation, it's in some way more clear what's happening here, okay? This one we know is loss, right? This one we know is the loss of your system. This one is the gain, right? You have something positive, something negative. This one we already know it's loss, so this one must be gain. Okay, and does it make sense if it's gain? Well, if you have larger nonlinear effect, it increase. Makes sense. If you have larger input, it also increase. Also makes sense. And the best part is if you compare this to the gain inside the waveguide. I think they're only mismatched by a factor of c because you're from waveguide to time domain. Okay, and let's just write down this. Okay, K1, K2 has omega 1, omega 2 here. So, and also this has a C here. So let's see. And then chi2. Okay. And let's compare the gain. Let's compare the gain from the waveguide. Gain from the waveguide is okay. And then this one is c squared, right? Mu naught, epsilon naught, c squared over 1. So when you look at this too, they're only off by a factor of c. Okay. So the gain you derived by using this method is the same gain you have in your parametric amplifier. Okay, so the entire thing kind of make a lot of sense. Okay, and The third method, I didn't put it in the note. For the third method, sometimes people also use that. Is previously we actually derived U1 and U2, the solution of U1 and U2. Okay. So, for example, we know E1Z proportional to, right? So they use this result and then say, okay, if you assume the solution is this of parametric amplifier, and this solution holds inside your cavity, okay, then this one will correspond to an equation like this, right? You have a gain. And then you change this into C and T, and then you minus your loss. Okay, then you will get exactly the same solution as here. Okay, so there are 3 different ways you can solve this equation. And normally, I'm not a big fan of the third way because sometimes it doesn't directly transfer from the waveguide or fiber solution to the cavity. It's much safer. Well, for me, I feel it's much safer, to start from here. Okay, and of course, this can work as a check, right? A third method check to check your result from here. Okay. Let's see. That's actually all from our note, and we have 10 minutes left. We can probably quickly go over the electro-optics effect you guys use in phase modulation, intensity modulation, and also in telecommunication, because that's a relatively simple thing, and then I don't want to spend the entire lecture on that. Okay, and let's do it here. So the electro-optics effect, written in this taught here would not be in the final exam because I don't have a note on that. Okay. Okay. So what's electro-optics effect? Electro-optics effect was actually discovered way before nonlinear optics, the concept of nonlinear optics. What happened is if you add a voltage on your material, you will see the refractive index change. Okay, and this should not be mistaken with thermal effect, because if you add voltage on anything, the refraction index change because you heat those things, right? You heat up those things. And the critical difference between thermal effect and this effect is thermal effect is very slow because it takes time to heat up something. Okay. So this one normally works. It's limited by the it's actually usually work at least to like 100 gigahertz. Okay, so you can apply a very rapid change. Let's say within 1 nanosecond, you flip the voltage, okay, and then the refraction index will flip. So be n refraction index equals n naught plus delta n is a function of the voltage you add here. And also we know that when you add a voltage, you add a field, right? The voltage create a field. Okay. So usually in theory you write down E2, but in experiment you write down volt, because you buy a phase modulator, they tell you how much volt it is to convert the phase from pi to 2 pi, or 0 to pi. So we write down E2 here, but remember in reality you use voltage. Okay. So this effect is kind of well known, like in a very classical picture. You can see how this can be turned into a phase modulator, right? We know K1 equals to n omega c, right? So equals to K naught the original one with the original refractive index plus this delta. Okay. So when you have a voltage on, your light is going to like this, I omega t plus I k naught c plus I delta n omega c. Also, we can write this down as okay, 2 pi lambda c. Okay. So you see, this is simply the phase with 0 voltage, okay, and then the refraction index change can give you a phase change here, right? And this can be quite large, because think about it, okay? If you change 1%, usually you can't. Usually it's I think 0.1%. Let's say 0.1% of your refraction index, then you only need to travel 1,000 times of your wavelength, right, to make it 1. And usually one wavelength is 1 micron. So if your device is 1 millimeter long, then you can already make a pi phase change. Okay. So this is the regular way of describing this effect, and it's good enough for everyday experiments. But also this can be unified into our picture. Okay, we have 2ik partial E partial C equals to right. This is our standard way of calculating the nonlinear effect, and the electro-optics effect is simply a very special case in sum or difference frequency, okay, depending on how you want to call it. Okay, so you can have chi2, and then say E times E2. Okay, you can simply have that. Oh, let's leave the T out. Okay, E2. And then when you do this derivative, you get 2ik. Well, actually, we don't even need to go through it. we know P equals to epsilon chi1 E plus epsilon chi2 E2 times E. Right? And then also we know N, I think it's N squared, right, equals to right. So well, you can write down your nonlinear effect like this. And E2 is just a voltage. It's just a field applied by a voltage. Okay. So you can now see you can do this P epsilon chi1 plus chi2 E2. Right? You can do this. What it looks like is that your E2, your field, or your voltage applied to your waveguide, change your chi1 a little bit, right? And that chi1 change your refractive index. Okay. So this is actually a microscopic view of how this effect happened. And when this would be useful, okay, you say, why can't I just do this? Why do I have to go through this? Okay. When is it useful? Is when you try to calculate this coefficient. Right? When you try to calculate this coefficient, then you need to look into the crystal structure. And then there's actually a quantum mechanical way to calculate this for each materials. And that one you can, without doing any measurement, you can at least predict how delta N2 would be. Okay. So that's the only use I can think about, okay, by unifying this effect into our nonlinear picture. Okay. Okay, so that's all for today. And then next week we only have class on Monday, and then that would be our final class on the second order nonlinear effect. After that, we'll move on to third order nonlinear effect, and that's more general. Every material has that, and then that's probably it. Okay. Yes.
So the E's on the right side, you have just E's with no subscripts. Is that the same as the E1 on the to the left in the center of the board there?
Yes. Yes, that's right. That's correct.
Okay.
Yeah. So it's just this is a light wave. This is
That's the
yeah, DC voltage. Yeah. Yeah.